Welcome back. Today we're going to be looking at what are known as linear equations of one variable, otherwise known as LEOVs, which is just an acronym. Most students will remember from maybe the 5th grade, perhaps the 6th grade, that at some point when you were learning your mathematics, you may have come across a problem where you might have 10 plus a box is equal to 30. And the point of this problem statement was that the student was supposed to figure out what number went into the box. Okay? And in this instance, we know that, or we could guess, that the number 20 should go into the box because 10 plus 20 is equal to 30. And we said that the number 20 was the solution to the problem statement. At some later point in time, students would recall that instead of getting a nice little box, the student would be asked to use the letter X to represent some unknown quantity. And if students were anything like me, when this transition occurred, a lot of students just didn't understand why instead of a box, we were replacing the box with a letter. Because the box, on the one hand, was very familiar in terms of the format, but then it just didn't seem like having a letter really added anything to the puzzle or to the problem statement, except that now instead of a box, you have a letter. And the second thing that you might remember whenever this transition took place is that probably every other middle school teacher that you encountered had a different way for solving these types of what are known as linear equation of one variable problem statements. Which of course led to a tremendous amount of confusion on your part if you were anything like myself, because it seemed like every teacher was asking you to do something different in order to solve a particular problem statement. What I'm going to teach you guys is a strategy for dealing with not only every single type of linear equation of one variable that you might be confronted with, but also dealing with algebra, problem solving, or what are known as equation balancing problems of any amount of complexity. And the strategy that I use is related to what is known as our inverse and or our identity laws. If you guys remember back at the beginning of the semester, we said that there was this thing known as an inverse law. And there are two different forms of the inverse law. Specifically, there is a form where it says if you, say, have a number such as the number 5, and you add its inverse, say, -5, you can add the inverse of a number on either side, and everything will add to 0. This is called the inverse law under addition. And at first, it doesn't really seem very useful. So this is the additive inverse law. Additionally, you'll recall that at the beginning of the semester, we have what is known as the identity law. And the identity law says that anytime you take a number, if you add it with your additive identity, and of course you can do this in any order, you'll get the original number back. And this seems rather straightforward and not really very important, perhaps, but it turns out that if you combine what is known as the identity law and the inverse law, along with what is known as the additive and or multiplicative properties of an equation, you can perform what is known as formula balancing for an equation, regardless of how complicated a specific equation might be. So this, in this instance, a plus 0 is equal to 0 plus a is equal to a. That is called the additive identity law. Okay, so before I can combine the inverse law and identity law to show you guys how we might go about, say, solving this 10 plus x is equal to 30 using this brand new technique. We need to discuss what is known as the additive principle of equations. And what the additive principle of equations says is it's just a remark about the basic idea of an equal sign. When you have some quantity, say a number is equal to something else, what we're saying here with the equal sign is that the number on our left-hand side has to equal the total quantity that exists on the right-hand side. And so if we consider this to be, say, a bank account, here's my bank account, and the bank account is our X in this instance, and we put $10 into our bank account, it just means that $10 is in our bank account. Now, what the additive principle of equations is saying is it says that anytime you have an equality, you may add in like parts across an equal sign, and that will maintain the balance of both sides of your equal sign. Said another way, if $10 is in your bank account and you deposit $1 to your bank account, then you've got, on the one hand, $11 in your bank account, but if the bank account itself was just labeled as X, then you added $1 to your X in order to get a bank account that now has $11 in total inside of it. Okay, that is the additive principle of equations. Our equation will remain balanced as long as we add in like parts on both sides of an equal sign. If we take the additive principle of equations, the identity law, as well as the inverse law, then what we can do is something very special. When you've got an equation like 10 plus x is equal to 30, and I want to, say, find out what my unknown number happens to be, obviously our unknown number has to be 20, right? Because the only number that we can add to 10 to equal 30 would be 20 itself. However, if we use a special technique of adding a specific amount on both sides of our equal sign, and in this instance, what we're going to add to both sides is going to be our additive inverse of the quantity that in this instance is next to x. If I add the additive inverse of a positive 10, which would in this instance be a negative 10, to both sides of my equal sign, negative 10 plus 10, that is going to be 0 according to the inverse law. Look at what the inverse law says. It says whenever you take a negative term and add it with its positive version, according to the inverse law, you're always able to obtain 0 at the end of the day. So if you took 10 and you added negative 10 on both sides of this equation, on the left side of your equal sign, you're going to get negative 10 plus 10. That just equals 0. But on the right-hand side, you'll note that you've got a new problem statement. You've got negative 10 plus 30. And if I owe you $10, but then I paid back, if I pay $30 into my account and pay back the difference, rather, I should have $20 in my bank account remaining. Now, according to the identity law, x plus 0 will just be x, because anything plus 0 is just that something. So, to be clear, when we started this particular process, we first used the additive inverse law on both sides of our equal sign. We then exploited what is known as the identity law to add x with 0. And what that resulted in is it gave us the solution to our equation, which in this instance is just kind of tune this portion of the video out, because they'll say, well, this seems rather superfluous. If I could just guess at the unknown number being 20, why would I go through all of these extra steps in order to find my answer? And the answer is, we're using a very basic example to demonstrate a principle. Usually, we don't dive into a complicated expression or problem right off the bat in order to demonstrate a very simple principle. You'll take something that is a very basic example, something that you could presumably solve in your head if you wanted to, in the most basic of circumstances, in order to demonstrate a more generic principle at hand. In this instance, we're demonstrating that using the additive inverse as well as the identity law will always allow us to solve a one-step LEOV additive case. So this is a special type of LEOV. It's called a one-step additive LEOV. Because you're using the additive inverse. Okay, let's have another example. The reason why the additive one-step LEOV problem-solving strategy is so effective is that it allows us to approach problems that are much more challenging. You might have 357 plus x is equal to negative 452. And while the previous problem, some students might be able to guess at it, in this particular instance, it's not exactly clear what the x should be. Students using mental math will, in fact, usually get tripped up by the fact that there is indeed a negative sign on the other side of your equal sign. But if we just remember the additive inverse law, we may add a negative 357 to both sides of our equal sign. So at this point in time, you'll get negative 357 plus 357, and of course that equals 0. But on the other side of your equation, you've got a situation where I owe you $357, and then at a later point I owe you $452 more dollars. So if we go to the side of our paper, 357 plus 452, we're going to add everything together. 7 plus 2 gives us 9, 5 and 5 is 10, carry your 1, 1 and 3 is 4, 4 and 4 gives us 8. So I should owe you $809 total. X plus 0 just gives us x, so at the end of the day, we have x is equal to negative 809 as our answer. Note that this principle is very useful in the sense that we may be adding, say, some negative fractions, such as 4 over 11 plus x is equal to 3 over 7. And just like before, where we may not have been able to, use mental math in order to determine what our x value happens to be, what we can do on both sides of our equal sign is we can go ahead and use the additive inverse. In this instance, the opposite of a negative 4 over 11 will be a positive 4 over 11. I'm going to add 4 over 11 to both sides of my equal sign, and we'll see what happens. You'll note that 4 over 11 plus negative 4 over 11, that's just going to give us 0. So you have 0 plus x. And on the other side of your equal sign, you've got 4 over 11 plus 3 over 7. X plus 0 is just x. So now we need to deal with that 4 over 11 plus 3 over 7. And what we're going to do is we need to find a common denominator. So we'll multiply by the opposing base. We'll multiply the first fraction by 7 over 7. We'll multiply the second fraction by 11 over 11. 4 times 7 gives us 28. 7 times 11 gives us 77. 3 times 11 is 33. 7 times 11 is 77. 28 plus 33. 8 plus 3 gives us, should be 11, carry the 1. 1 and 2 is 3. 3 and 3 gives us 6. So we should have 61 over 77. And that is what our x is going to be equal to. All right. And of course, that would have been nigh impossible to do in your head. But of course, the one-step LEOV problem-solving strategy also extends to decimals. So if you have something like negative 752 plus x is equal to 0.534, if you will, then just like before, where we can use the additive inverse on both sides in order to solve for our x, we can do the exact same thing here. I'm going to add 0.752 to both sides of our equal sign. What will happen is 752 plus negative 752, that's just going to equal 0. And then on the other side of your equal sign, you're going to have 0.752 plus 0.534. 4 and 2 is 6, 5 and 3 is 8, 7 and 5 gives you 12. So you get 1.286. X plus 0 is just x, so you get your answer, 1.286. So this technique of solving a one-step LEOV turns out to be incredibly powerful. We can use this particular strategy if we're dealing with decimals. We can use this particular strategy if we're dealing with fractions being added to an unknown number. And we can use this particular strategy for anything in between, including negative numbers. Now, unfortunately, students will recall that this isn't the only type of problem-solving strategy that you probably encountered in, or not problem-solving strategy, but problem statement that you encountered in your lower-level math classes. And in fact, you'll probably also remember 2 times a box is equal to some number. You might remember a problem statement such as 2 times the box equals 20. And then the student was asked to fill in the box to figure out what the quantity, what the unknown number happened to be. And in this instance, 2 times 10 equals 20, or said another way, 10 is the only number I can multiply 2 by in order to obtain 20. And so my unknown number must be 10. So that would be our solution to the problem statement. At some point in time, your teachers moved away from using the box. You may remember 2 times x is equal to 20. And some students would remember that a teacher would ask them to divide both sides by 2. Right? And the problem with division on both sides by some amount, even though you can indeed calculate the answer in this particular instance, is that division, much like subtraction, is what is known as an operator that is not algebraic. And what it means is that you have to be very, very careful that you're not violating either the distribution law or the associative law whenever you divide both sides of a specific equation by some number. So for example, if you had 2x is equal to 15 plus 20, and you divide by 2, oh, I divided by 2 on both sides, right? Didn't I get the correct answer? This would be an example of violating what is known as the distribution law. So while you could divide on both sides, because you didn't divide on both sides correctly, you're going to obtain an incorrect answer. In fact, if 2x is equal to 15 plus 20, the way you know that that operation was incorrect is that you could have added 15 and 20 together. That would give you 35. And then if you had divided by 2, your answer should have been 35 divided by 2, which should be 17.5. Whereas here, when you divided 15 by 2, well, 15 divided by 2 is 7.5. And if you add 7.5 with 20, you get 27.5. And clearly, these are 2 different answers. So one of which has to be incorrect. This is why, this is one of the reasons, or one of the primary confusions that students encounter, where I would tell students, look, we're going to avoid what we learned in middle school math. We're just going to forget everything we learned. We're going to start all over. And this time we're going to learn how to do things correctly. And by correct, I mean using the rules of algebra. And for that, we're going to go back to our inverse law, but this time we need to consider the inverse and identity laws for the multiplication case. If you recall, for the inverse law under multiplication, What it says is, it says anytime you take a number and multiply it by its inverse, which is 1 over that number, you're always going to get a number divided by itself, which just equals 1. So you can take a number, any number you want. If you multiply it by 1 over that term, you're always going to get 1. Just as an example of that, 2 times 1/2 will give you 2 over 2, which gives you 1. If you did 3 times 1/3, you get 3 over 3, which gives you 1. Any number times 1 over itself always gives you 1 under multiplication. And then there's also the multiplicative identity law, which we're going to need to use. And the multiplication identity law just says that if you take a number and multiply by 1, you can do this on any side of the number itself, and you always get back the original quantity. So just as an example, 3 times 1 is the same thing as 1 times 3. That gives you 3. 7 times 1, same thing as 1 times 7, gives you 7. 10 billion times 1 is the same thing as 1 times 10 billion, which just gives you 10 billion. All right. Now, using these two rules, as well as what is known as the multiplicative property of equations, we will be able to solve this linear equation of one variable, multiplicative case, using the rules of algebra. But first, we need to know what the multiplicative property of equations happens to be. For the multiplicative property of equations, it simply says that anytime you have a number equal to some quantity, if you were to take both sides of your equation and you scale it by some amount, and by scale I mean multiply that by the same amount on both sides of the equation, the quantity remains unchanged. The quantities inside of the equation itself that may be unknown in particular remain unchanged. You'll note that we started with an equation that read an unknown number is equal to 10, and when we doubled both sides of our equation, when we said 2 times the unknown number is equal to 2 times 10, what happened is you get a new equation, 2 times an unknown number is equal to 20. But just as before, you'll note that 2 times the box is equal to 20, and 10 must be the number that exists inside of the box. And this, of course, holds true for any amount that you scale an equation by. So if you were to take the same equation and, say, multiply both sides by, say, 3, your unknown number remains unchanged. The unknown number now exists in a new equation, a third equation, where we've got 3 times the unknown number is equal to 30, but, from our box method, you guys will remember that the only number that can go into this box happens to be the number 10. So our equation largely remains unchanged. So we're going to use that general idea in order to solve these linear equation of one variable, one step problem statements using only the rules of algebra. What I'm going to do is I'm going to start off by picking a number that I can multiply both sides of my equation by. What I want to do is I want to remove this number, this coefficient that's in front of my x value, that's in front of my unknown number. Because when I solve for x, what I'm trying to do is I'm trying to transform this equation and get it to look something like this, where you've got x on one side of your equal sign and everything else grouped on the other side of your equal sign. So what we're going to do is we'll go ahead and we'll multiply specifically by the inverse of a number. So I'm going to find the inverse of 2, which happens to be 1/2. And if I multiply on both sides, magic is going to happen. 2 divided by 2 on the left-hand side, and we'll have 20 divided by 2 on the right-hand side. Now, 2 divided by 2 is very special because that is always equal to 1 according to our inverse law. And then 20 divided by 2 gives us 10. So ultimately, you'll have x times 1, or x, is equal to 10. And voila, that is your answer, which we already knew from before had to be the case. But now we have a problem-solving strategy where we can solve any number of problems according to the rules of algebra and obtain an answer. By the way, just as an aside, the way that you obtain an inverse of a specific quantity is you just imagine in your mind flipping the quantity into the denominator of a fraction. So if I wanted to find the inverse of 2, I need to take 2, flip it into the denominator of a fraction, which gives me, of course, the number 1/2. This is called the reciprocal of 2, otherwise known as the inverse, multiplicative inverse of 2. All right. Moving on to a more challenging case, suppose you have 153 times an unknown number is equal to 744. Obviously, we can't solve this problem in our head, right? We can't really solve the problem in our head. So what we're going to do instead is we will multiply both sides of our equation by 1 over 153. Because I take 153 and I find its reciprocal, which in this instance will just be 1 over 153, multiplicative inverse of 1 over, the multiplicative inverse of 153 being 1 over 153. So then what happens on the left-hand side, just like before, you'll get 153 times 1 in the numerator, or just 153, and 153 in the denominator doesn't change. So I'll have 153 over 153. But then on the right side of my equal sign, I've got 744 times 1, or 744, and that's going to be over 153. So 153 divided by 153, that just gives us 1. And then on the right side of our equal sign, we've got 744 over 153. X times 1, of course, being x, and I get x is equal to 744 over 153. And that is our answer. Now, this method works if we have fractions, a bunch of nasty-looking fractions on both sides of our equal sign. If you have something like 3/4 x is equal to 7 over 11, just as before, all we have to do is take our number that's in front of our x, and we're going to think about what happens if I throw it into the denominator of a fraction. So now you'll have 1 divided by 3/4, and of course that gives us 4/3. Said another way, the reciprocal of a fraction is always just flipping the fraction over on itself. And so the number that I need to multiply both sides of my equal sign by, in this instance, if I wanted to solve for x, would happen to be 4/3. So I'm going to multiply 3/4 x by 4/3, and I'll multiply 7 over 11 by 4/3. Now, what's interesting is when you pick the correct reciprocal, and you multiply both sides of your equal sign by that specific reciprocal, the coefficient that's in front of your x is guaranteed to be forced to be 1. Because what will happen is when you multiply across the top, you got 4 times 3, which gives you 12. But then when we multiply across the bottom of our fraction, we have 3 times 4, which also gives us 12. So now you've got 12 over 12, or just 1 times your unknown number, is equal to, well, now we're going to multiply across the top and the bottom again. 4 times 7 gives us 28. 3 times 11 gives us 33. So now I've got 28 over 33. So in conclusion, my answer will be x is equal to 28 over 33. And of course, this system works if you are dealing with decimals just as well as it works for anything else. If you have, say, 0.75 times an unknown number is equal to 1.25, then you want to figure out what this is. You're just going to take your number that's in front of your x you pretend to flip it into the denominator of a fraction, and then you're going to take that term and multiply it on both sides of your equal sign. So now I'll take 0.75 and multiply it by 1 over 0.75. And I do this on both sides of my equal sign. So you get 0.75 divided by 0.75. X is equal to 1.25 over 0.75. 0.75 divided by itself just gives you 1. So I got 1 times x is equal to 1.25 over 0.75. 1 times x just gives me x. So x is equal to 1.25 over 0.75. And that's really all I have to do. Now, of course, you would have to finesse, if you wanted to actually know what this is equal to, you're going to have to finesse this particular situation and recall division of decimals. So we can, in fact, if we want to, we can count the number of decimals behind the decimal place. You'll note that you've got 2 digits on top, 2 digits on bottom. So if you multiply by 100 over 100, we can move the decimal place 2 spaces to the right, and we get an equivalent fraction, 125 over 75. Now, with this 125 over 75, you can go to the side of your page. Although 125 is the same thing as 5 times 25, and 75 is equal to 3 times 25. So you've got 5 times 25 over 3 times 25, and the 25's cancel out, and you've got 5/3 is your answer. If you were so inclined to actually calculate this out and you wanted a fraction, 5/3 is a good answer there. Or if we wanted a decimal, which we probably do if we're dealing with decimals, we just go and we do 3 into 5 goes 1 times 3 is 3, subtract, you get 2, drop your 0. 3 into 20 goes 6 times, 6 times 3 gives you 18. Subtract, so you get 1.666666, continuing, and that would be our decimal approximation. So however you want to do it, ultimately dealing with the decimal math is a separate issue from actually calculating what x must be equal to. At this point over here, if you had done 1.25 over 0.75, that would have been an okay answer for many engineering classes. Like, honestly, it doesn't really matter at that point because we can punch it into a calculator if we were so inclined to do so. But if we really wanted to know what the calculator was doing, recall back to your decimal manipulations and just know how to convert, say, the decimal answer to its equivalent fraction form, or be able to resolve the decimal to a decimal approximation and obtain, say, 1.666. Now, the reason why we want to lay the foundation for solving LEOVs using what are known as one-step LEOV problem-solving statements is that, in general, the types of equations that you will be given in many instances are going to be what are known as two-step LEOV problems. And a two-step LEOV problem will be very similar to a one-step LEOV problem, but it just basically is going to require you to solve a more involved version by basically taking the techniques of both the additive and multiplicative LEOV one-step problem statements to the next level. So a two-step LEOV problem will look like the following. You'll often have, say, some unknown number times something plus something else is equal to something. And the question is, solve for the unknown number. Okay. So we've got 5x plus 10 is equal to 20. How do we solve for the unknown number? What we are going to do is we will use what we understand from solving the one-step LEOV problem-solving strategies, and we're going to combine both the multiplicative and the additive cases in order to solve this particular problem. However, we're always going to start with the addition operation, since addition is usually going to be the easiest thing that we can do. So if I want to start solving this equation, I'm going to add the additive inverse of 10, which will be a negative 10, to both sides of my equal sign. You'll note that 10 plus negative 10 gives me 0, so I get 5x plus 0 is equal to, and then 20 plus negative 10, that should give me just 10. 5x plus 0 is just 5x, and now we have a one-step LEOV multiplication case. And so for the one-step LEOV multiplication case, what we know is we can multiply both sides of our equation by the multiplicative inverse of whatever number happens to be in front of our x. So the multiplicative inverse of 5 will be 1 over 5. And of course, when we do the fraction multiplication, we get 5 divided by 5. And on the other side, we get 10 divided by 5. 10 divided by 5 is 2. 5 divided by 5 is 1. So you get 1 times x is equal to 2, or x is equal to 2. And that's our answer. Of course, the LEOV two-step problem-solving framework works in the instance that you might be dealing with much more complicated problem statements. You might have, say, negative 35x plus 175 is equal to 255, and the question, of course, asks you to solve for x. And what do we do? Well, if we follow the strategy that we were using earlier, we're going to start by attacking the addition operation with our additive inverse. We're going to use the additive inverse of a positive 175, which will be a negative 175. We'll add negative 175 to both sides of our equal sign. This will allow us to add to 0. We get negative 35x plus 0 is equal to 255 minus 175 on the other side of our equal sign. 255 minus 175. 5 minus 5 gives you 0. And of course, you got to borrow a 10. 15 minus 7 is going to be, let's see, 8. Okay, so you get 80 on the other side of your equal sign is equal to negative 35x. And now you can use the multiplicative inverse of a negative 35, which will just be 1 over 35. Since it's negative, your multiplicative inverse will also be negative. So I'll have a negative 1 over 35. You got to do what you do to one side, you got to do to the other as well. So you got to take your negative 1 over 35, and we have to multiply this with the 80 as well. We can't just do it to one side. So this will just clean up nicely. It'll be negative and negative is a positive. 35 times 1 gives you 35. So we'll have 35 over 35. X is equal to, on the other side, you've got negative and positives and negative. 80 times 1 is 80 over 35. You get 1 times x is equal to negative 80 over 35. And 1 times x is just going to be x. Now, 80 over 35, what happens here? That's the question. What happens here? All right, well, we can say that 80 is the same thing as 8 times 10, right? And 35 is the same thing as 5 times 7. Of course, we could clean up this 8 times 10. It's going to be 8 times 5 times 2. And that's probably the best we can do for this situation. So you've got negative 8 times 5 times 2 over 5 times 7. You can cross out the prime factors being 5. You've got negative 8 times 2 gives you 16, and all over 7, and that's your answer. Do not feel like you have to get a decimal approximation for your answer. In fact, it's much more likely that a fraction will be, in fact, a nicer answer to deal with. All right, so in summary, we start with the additive case of a one-step LEOV. Okay? And what we say for the additive case is that anytime you have an unknown number plus something is equal to something else, we can clean this up by adding the opposite of a given number to both sides are equal sign, and that allows us to exploit the additive inverse law, and you'll just get b minus a on the other side. So we get x plus 0 is x is equal to b minus a. Always, always, always. That's always going to be the case for a one-step LEOV under addition. And then we consider what happens when we have a one-step LEOV under multiplication, where you might have a number times something is equal to something else. And we said that anytime we have a LEOV under multiplication for these one-step problem statements, you can just take a number, you multiply its inverse on both sides of an equal sign. And then what happens is that by the multiplicative inverse law, you get a number divided by itself, which will just give you 1. So the coefficient in front of x is almost as if by magic transmuted into the number 1. And you get x is equal to b over a. All right, for the two-step LEOV, what's going to happen is you start with ax plus b is equal to something else, just like this. And we start solving these two-step LEOVs by first using the techniques developed in the additive one step. So we're going to attack the addition operation by adding the opposite of b to both sides of our equal sign. So you got b plus a negative b, that's just going to give you 0. And then on the other side, you have c minus b. ax plus 0 is just ax, so you have ax is equal to c minus b. Now, at this point in time, you want to clean up the number, the coefficient in front of your x. So just as before with the multiplicative case, you're going to multiply 1 over a on both sides of your equal sign. Now note, however, when I do this, I have to be very careful. 1 over a times a, that's going to give me a over a times x, which is what I'm looking for. But on the other side of your equal sign, you'll note that I have a set of parentheses around my c minus b. That the parentheses are important. They're critical. I need to have a set of parentheses around my c minus b term. I can't just multiply 1 over a by c or 1 over a by the b. This is a big mistake that I see students making in Math 950. If you do that, you are just wrong, okay? You got to multiply 1 over a by everything on the other side. And how we designate everything on the other side is by using a sequence of parentheses. So your answer will be 1 over a times c minus b. A divided by a cancels out, and you have c minus b times 1, or c minus b all over a. So x is equal to c minus b all over a, and that's your answer. Students who are watching this video should understand each and every step of this specific process, because if you don't, you can't just make it up when you go to take your examination, okay? I've seen students who tried to wing understanding kind of sort of what I'm doing, and then they go take the examination, and I'm going to give them a problem which tries to test their understanding, and of course, usually where they make a mistake is with the multiplicative inverse on both sides. They really don't understand why they need to use a set of parentheses on the right-hand side or equal side. They really don't understand when they use a multiplicative inverse. Students should know that while I started this two-step LEOV process by adding the inverse of b on both sides, I could have started it by using a multiplicative inverse instead. Consider this previous example problem. Negative 35x plus 175 is equal to 355. While it's true that, in general, the way I solve things is using the most easiest and convenient method available, which will always be to attack the addition or subtraction operation first, it is true that you could have used a multiplicative inverse. And so if I used a multiplicative inverse of negative 35, which would be negative 1 over 35, then all I have to do is I have to remember that I'm going to multiply this negative 1 over 35 by everything on the right-hand side of the equation, as well as everything on the left-hand side of the equation. So you need to set up your equation statement like so. If you wanted to multiply this negative 135, you're going to multiply across the entire term, not just with your 35, your negative 35x. So you've got to do negative 1 over 35 times 175 too. And then on the other side, obviously, what you do to one side, you have to do to the other side. Now, the reason we don't recommend this procedure is that you're just going to really complicate solving these problems, and it's a sign of a novice to give yourself more steps than what you really need in order to solve a particular statement. Because now, I hope everybody can see you've got this really ridiculous problem statement where we've got negative 175 over 35 is equal to negative 255 over 35. Now, if we didn't clean up this fraction and all we did was we used our additive inverse at this point in time, what we can do is we could add 175 over 35 to both sides of our equal sign. And I have seen students do this. So you're going to get 0 plus x is equal to negative 255 plus 175 over 35. And that will be, of course, negative 80 over 35 when you simplify that out. So you get x is equal to negative 80 over 35. Now, the question, of course, is, and that's not the answer, it would divide out and be negative 16 over 7. The question, of course, is, do you want to go through all of these steps to do the same thing that you did before? Because typically speaking, what we tell students is each single step is critical, because every single step that you do or that you take in a specific problem statement is one more opportunity to make a mistake. It's one more place where we could drop a negative sign. It's one more place where our 6 can become a 7 or a 9, or a 1 could become a 7 if that's ever happened to you. And so we just recommend students stick to problem-solving methods that will obtain the fastest result, as opposed to just purely relying on knowing and or understanding the rules of algebra in detail. It's not to say that you can't, say, start the solution of a two-step LEOV problem statement by using your multiplicative inverse. It's just that it's going to introduce a lot more steps and perhaps convolute the answer a bit in such a way as to where a lot of students, or perhaps I dare say the majority of students, would then begin making a mistake somewhere. And all else being equal, if you value not making a mistake, if you value, say, making 100 on your examination, it behooves one to just know what are the standard methods by which you solve a two-step LEOV. And the standard way that we solve the two-step LEOV is going to always begin with adding the inverse of a number on both sides of their equal sign, and only then using the multiplicative inverse on both sides. All right, guys, and with that, I will let you go. Take care. See ya.